And thanks a lot, Matthew, for the talk. It was really great. During the talk, there were some questions that you have answered. I think in the interest of people who may have missed it and for recording, maybe we can repeat the answers very quickly. Just to go over it, Brian Dolan asked whether a physical boundary represents something in the physical model, like a wall, and what is an interface boundary?
Yeah, sure. I'll clarify the answer. So basically, so the physical boundary condition is in terms of external aerodynamic simulation, like we do for aircraft. It represents a wall, so that would be the aircraft itself. Also, it can be a symmetry if it can be a far field boundary condition. So all really physical meaning conditions that we need to model for the problem at hand that we're trying to solve. And the interface boundary is really just a virtual boundary that is created by us when we are dividing the domain, because it's not really a boundary conditions. It's just that since we're separating the flow, we're also separating the elements, but when we're solving numerically the equations, we need flow quantities for all the neighbors, but we're creating separation in the computational domain. So we need to add those special interface between zones that we need to perform communication between the zones. And so that's the difference between the two.
All right, thanks. And we have two more related, I would say, questions on Q&A, if you can see them. I'll just briefly summarize them in my own words. I hope I can characterize the question right. One is asking like productivity comparisons between CHIUW and SU2 in terms of code size and complexity. Have you done anything like that?
No, not yet. We haven't done that, and it's something that we're really looking for in doing. But the thing is, it's really difficult to do because, like I said, even though they're both solving the same equation, our implementation is what we call a cell-centered implementation, while SU2 is a cell vertex implementation. So it does require some significant differences in some algorithms. And so it's really complicated to compare really one code to another, especially in terms of complexity. And so, but in terms of flexibility, that's something that we're looking for in comparing in other codes for sure. But for now, we haven't done that comparison yet.
Okay, thanks very much. And as far as I
was going to say, there's an interesting question to me on the chat Q&A from one of the other speakers. Just a really quick one, I think. Is the Chapel code open sourced for Matthieu's work?
No, sorry. Unfortunately, it is not open source, but we started some discussion about that lately in the lab. But it's always been complicated with our lab to make our application open source. But we're discussing it. But for now, it is not open source.
Okay, thanks.
The next question in the Q&A is what led to CHIUW to use coverall plus on plus coverall plus local, sort of like an SPMD approach. I think you alluded to this a little bit, but maybe you want to clarify why didn't you use higher level approaches and just used coveralls?
Well, we try different approach, and what I presented today was the one that provided us the best overall performances, and really try to mimic what is done in a typical SPMD approach, as I explained really briefly in the presentation, and so this is really just because of performance concerns, really.
Okay. Thanks again for the great work and the great talk. Really exciting stuff.
Thank you. I think there's another question from Brian. I don't know if we have time.
Oh, yeah. We have 1 more minute.
Okay, so the question is, did you write the solvers for the gradients in CHIUW and Chapel, or did you use the C libraries? And so everything is written in Chapel except for the linear solvers for GMRes and BCGSTAB, which are provided from PETSI. But the symmetric Gauss-Seidel solver is implemented in Chapel. And for the gradient, we have two implementation in Chapel. We're using a Gringoss approach and also a weighted least square approach.
All right. Thanks a lot, Matthieu.
Thank you very much.